I'm going to talk about a different modeling approach that we are working on in parallel to the work that RIMPL is doing with others on SSRS and also the Bayesian modeling approach that you'll hear about next. But this is another approach that can also be integrated into the same model framework that we have already developed for SSRS. So we're calling this a heuristic agent-based movement model. The idea of heuristics is a method that, in computation, a method that is efficient at providing a solution or an approximate solution. So the tool that we have that RIMPL just presented is best suited for, I would say, modeling wind farm scale movement patterns and larger movement patterns, and based on solving this fluid flow problem. When we get to looking at finer scale movements at a very detailed scale, perhaps around an individual turbine, we're going to need a different, more explicit approach. And that's what we're hoping this can provide. So it's also got to be practical in terms of, all of the tools that we're developing will have to be efficient in terms of computational power and so forth, the ability of other folks to run those in reasonable timeframes. The other piece that we really need to work here on incorporating is the thermal lift field, and Regis already presented our approach to how we're going to develop those fields, which are difficult to model and simulate, but really critical to this work because for birds like large soaring birds like golden eagles, thermal lift is what's most widespread and most readily used. Orographic updraft certainly used when available, but thermal convective lift is something we really have to build into this. And the tracks that you get when birds are using thermals are quite different in structure than a bird that's moving along a terrain feature where they're using orographic lift. You get these sequences of soaring and gliding, and that's what we would really like to be able to simulate. So this idea is really motivated by a lot of observations of eagles in flight, particularly during migration, as well as telemetry data. And the idea is to encode the rules or fine-scale decisions that a bird might be making as it exploits lift that's available to it, both orographic and thermal lift. And this, I wanted to show these tracks. This is telemetry data, approximately 1 minute resolution. And these two birds, these are two individual golden eagles, a male and a female, moving down the same terrain features about a month apart, and really remarkably similar tracks. So they're moving, part one up here, they're moving along a ridge top. The area labeled 2, the birds are crossing over. This ridge is falling away and they're crossing over to a higher ridge. Then they navigate this river, this water gap here at 3, and then they both moved more to the windward side of the ridge after making that movement across the water gap. So when we see sort of stereotyped behavior like this, it I think leads credence to the notion that we might be able to come up with a way to simulate this. Certainly, eagle flight behavior is complex. There's a lot going on there, and we can't simulate all the fine details of all the decisions that they're making on the fly, but I think we can do some of that. So recently I discovered this track. This is 8 years later, different bird. This is a female. This is November, doing almost exactly the same thing. Now this is more another generation of telemetry units. So this is 6-second data. So we can actually see some of the really fine scale features of what they're doing. So there is one detail that I'm showing here where the birds coming down this region actually thermaled for a little bit to gain height before crossing over. So there is the sort of like the more detail we look at these tracks, the more interesting behaviors we're capable of seeing. Even with 6-second data, we can't quite resolve this track, but you can certainly see the bird is circling here. And I've looked at the altitudes and it's actually gaining altitude here. So it's using, it's circling up in an updraft there to cross over. Okay, so this is a bit of a complicated slide, but essentially what we have is this rule set that is applied iteratively as the bird moves through the domain. And so it works on the updraft field and the thermal field. And so we're starting up here. There's a search arc. The bird is looking out ahead, a 50-meter arc, and sampling that region and picking a location where there's updraft. Now, this is oriented along what we call principal axis of migration, or the direction of flight, essentially. And there is some stochasticity there, plus or minus 15 degrees. And so if it finds available updraft, it then moves to that position. And so that can repeat. But if it doesn't find available updraft, we also have what we call a look ahead search that it can do. So it can look out beyond the 50 meters to look for regions of higher lift and move in that direction. Now, if the bird happens to find a thermal, what it will do is it goes into a different movement there, what I call the thermal soar glide movement. So it centers itself into the middle of where that thermal lift is, and then it does a soaring movement. So you see this sort of a corkscrew. The reason it does it's directional is because it drifts with the wind. So these thermals often drift with the wind. So it will soar up and then glide and then continue its movement. So we have a sequence of these movements that the bird is using as it moves through this gridded domain. Now, in addition, it can do random walks. This would be to replicate, interacting with another bird perhaps, or foraging for food or something like that, that aren't directional. So there's this sequence of different rules that can apply as the bird is moving through the domain. And they are hierarchical. So it starts with the simple search 50 meters out before it starts these other potential movements. I will talk about this more later in the more hands-on session if people are more interested in how that all works. But these are so it then is using these updraft fields. So on the left, this is using the simplified model. Regis talked earlier about improvements that we're going to make to this. For the time being, as a placeholder, I'm just using a randomly generated field of thermals with spacing guided by 1.5 times the boundary layer height. We will replace this with Regis's work with the Allen model that is just about finished now. So what we can then do is generate a sequence of tracks similar to the way SSRS does. So in this case, I've put the entry points on the northwest boundary. This is southward flow migration. This is the same region that we have some telemetry data for. These little offset squiggly things are the winds from the northwest, so the bird encounters the thermal and circles up and then glides off. And so it's circling up and being drifted by the wind. That's these funny little pieces that are at 45-degree angles to the main flow. We generate a presence map similar to what Rimple has already presented. And I think you can see this is the data up here. This is the presence map here. Now we have some birds that are traveling down this other ridge over here. So there's some high presence there. But this shape here is fairly close, I would say, to the shape that is shown in the telemetry data. This is about a minute to run. So this is pretty efficient. Now, the one thing I've done differently with presence is we've assigned some weighting factors to these different moves. So if the bird is using orographic lift, we give it a weighting of 1. A random walk, which would generally be at lower altitude, we give a weighting of 1. So other moves are half. And then the thermaling move, a bird first locates the center of a thermal, we give that a half. And then as it circles up, we have a rapid decay, exponential decay of this weighting factor. And then it glides and the weighting factor increases linearly as it glides back to 0.5. So this is, somewhat ad hoc, but it's a way of, in the meantime, accounting for the height or the altitude of the movement, so that we're not, if you don't do this, you get a lot of weighting to these circular movements because there are a lot of movements in a small space, but we know that they're at high altitude. Okay, so that's pretty much it. There's a lot of ongoing work to incorporate the more realistic thermal and updraft fields into this. The other thing we want to do is, because just going back to this slide, this is a random realization. So what we really want to do is run numbers of tracks over many realizations of the thermal updraft field to get more realistic presence maps. And so this is a work in progress, but I think I'm pretty happy with the way it's going. Of course, when we move to an area like Wyoming that doesn't have this structured terrain that we see in the Appalachians, where most of the work so far has been, we have to develop some different rules in terms of local movements, say, throughout a wind farm like top of the world.